x, right? That's the function that when I evaluate d minus 3i on that, I get 0, right? So if you look at the red and you look at the blue, do we need both of these? We just need one, right? Because either one of them has both the sine and the cosine, right? So keeping both 3i and minus 3i, it's redundant. So it turns out, in these problems, whenever we have a conjugate pair, we just pick one of the pairs and write down the complex solution for that pair and keep the real and imaginary part for our solution set. And we just ignore the conjugate. It doesn't matter because we already have what we need for one copy of the complex root. Of course, the last two are easy, right? This gives me like an e to the minus 3x, and this gives me an e to the 3x, yeah? So from all this, I'll get to the point. Let me give this a name, Pac-Man. So Pac-Man solved by y equals to c1 cosine 3x plus c2 sine 3x plus c3 e to the minus 3x plus c4 e to the 3x. This is to be expected that we have 4 constants because this is a 4th order problem. All right? Now, did you guys enjoy this thing we just did with factoring in the complex numbers? No. It's probably wise for us to develop a little theorem that we can just use so we don't have to go through this rigmarole every time that we come across a complex factor, right? So let me do that for you guys. So here's the deal. Well, how do you decide whether or not a polynomial has complex roots or not? Like, what's the methodology there? Do you guys know? What can you tell me about polynomial factoring? Is it hopeless? Can we factor polynomials? Like, what's the deal? What's the general story? We can factor polynomials. So there's like always a quadratic formula. I mean, there's a quadratic formula for quadratic polynomials, right? That'll essentially factor it, right? What about cubics? Is there a cubic formula? There is actually. Is there a quartic formula? There is actually. Is there a quintic formula? That's a trap. That's not true. Actually, that's the birth of group theory. It took mathematicians the better part of about 50 years to prove that there was no such thing as a quintic formula, and that ultimately laid the groundwork for what we call group theory today. So it turns out that there is no general formula to write down the solutions to the polynomial equation equal to 0 if you're order 5 or higher. There simply does not exist a formula in terms of roots, sums, differences, and so forth of the coefficients which define the function. Yet, nevertheless, there is the fundamental theorem of algebra, which says that if you've got a polynomial equation of order n, there are always n complex zeros possibly repeated. So despite the fact that I can't write down a formula for the roots in terms of the coefficients, like the quadratic formula, in general, we do have hope that the nth order polynomial equation has n solutions possibly repeated, which means that if we have an nth order constant coefficient problem, there are n choices of lambda possibly repeated. And for each one of those, by the lemmas we talked about today, we have a solution, which means we just write down a linear combination of those solutions and we solved it. So really what I'm telling you is to solve the nth order problem, it is the same, in some sense, as just the problem of can you factor the equation which corresponds to the differential equation, right? So you've already seen that at play in the examples here. I need to give you a lemma though. So here's the other lemma. If, well, let's just say this, the operator d minus alpha quantity squared plus beta squared has real solutions, I guess I should write it this way. My bad. The differential equation. Okay. This acting on y equals to 0 has real solutions. Y is equal to e to the alpha x cosine beta x, and y equals to e to the alpha x sine beta x. So y1 and y2. And by the way, those are linearly independent. Which is to say, anytime we have a irreducible quadratic in the factorization, it begets to us a pair of like sine and cosine solutions. Correspondingly, the differential equation d minus alpha quantity squared plus beta squared squared equal to 0 has real solutions. Y1 equals e to the alpha x cosine beta x, y2 e to the alpha x sine beta x, and guess what? Y3 x e to the alpha x cosine beta x, y4 x e to the alpha x sine beta x. I've proved enough today. I'll maybe prove that like next class or something. Let me just show you some examples of this rather than proving this at the moment. So like example 7, suppose we want to solve let's see here. We'll look at 3 different things. Y prime prime plus, 3y prime minus y equals to 0. And part B, we'll look at y prime prime plus 4y prime plus 5y equals to 0. And part C, we'll look at y prime prime minus 6y prime plus 9y equals to 0. So each one of these, I'm going to illustrate a method for you guys. That method is called completing the square. We can factor a polynomial by completing the square. How do you complete the square? Well, I guess one step at a time, right? I guess I already moved it. Maybe you moved it. I don't know. Okay, so the first one's kind of ugly. But here's how it goes. This is, yeah, really. So d squared plus 3d minus 1, I can rewrite that as d minus 3 halves, quantity squared, minus 3 halves squared. And I've still got the minus 1, right? So what that is d minus 3 halves squared minus what? That's a 9/4 minus 4/4, also known as minus 13 over 4, I think. Right? Whenever we have the difference of squares, we can rewrite this then as d minus 3 halves plus the square root of 13 over 2. And then d minus 3 halves minus the square root of 13 over 2. So if after completing the square, we have a subtraction, then we can use this a, what is it?
We can go from d plus 3 halves squared to d minus 3 halves squared.
That's completing the square. So, so this is lambda equals to 3 halves minus the square root of 13 over 2, and this one is lambda equals to 3 halves plus the square root of 13 over 2. Remember, we have to compare to the pattern d minus lambda, right? So the first part A, the solution, is y is equal to like c1 e to the 3 minus the square root of 13 over 2 times x plus c2 e to the 3 plus the square root of 13 over 2 times x. There you go. That's the solution for part. That's for part A. Part B turns out much easier. well, I guess it's, I don't know, the completing the square is easier here. So check it out. So d squared plus 4d plus 5. I know you're like, what is completing the square? So completing the square is we take whatever's the coefficient of the linear term, right? And we half that. And we add it to d in this context, and we square that. When I do that, that will recreate the d squared and the 4d, right? But what else does it do? This does what? This also adds 4, right? So to be fair, I have to subtract 4. And I've still got the plus 5. So what I got here is d plus 2 quantity squared plus 1. So then, this is exactly the context of the lemma. See? This is the context of the lemma. We have alpha equals 2 minus 2, and beta is equal to 1. Therefore, the solution is the following. C1 e to the minus 2x cosine x plus C2 e to the minus 2x sine x, and there's your solution for part B. Completing the square for part C is kind of silly. We've got d squared minus 6d plus 9. What happens when we take half of 6? We got d minus 3 squared minus 9 plus 9. Oops, that's just d minus 3 squared, right? So therefore, my solution is c1 e to the 3x plus c2 x e to the 3x. So this example illustrates all the possible solution types of a quadratic. You either have a distinct real case, a complex case, or a repeated real case. And this is the structure of the solution set in each case, every one of which can be revealed by just polynomial factoring. So, isn't it stupid how easy these are to solve? I mean, maybe you're not used to it yet, but if you take a step back, all I'm saying is to solve the nth order problem, we just have to factor the polynomial that corresponds to the problem and write down the answer. It is amazingly simple. Yeah.
How did you get alpha equals negative 2?
Oh, comparison.
Solving it for 0. Okay.
Yeah, just compare, because we have to compare, you have to compare. It's d minus alpha. So when I look at this d plus 2, that makes my alpha minus 2. But anyway. So thanks, guys.